Hello everyone. I am Professor M.N. Mistry from DKT Society Textile and Engineering Institute, Itsalganji. I'm here to start or commence our further session of FDP 4, session number 8. Our resource person is evening personality, Miss Sweta Manjare Madam, who is going to present FDP session on predictive maintenance and fault diagnosis in EVs using machine learning. Before going to the session, I would like to introduce our today's guest, Ms. Sweta Manjare Madam. She is seasoned electrical engineer professional and a PhD research scholar. She is having 16 plus years of rich industrial and consultancy experience across power systems, switchgear and protection, and renewable energy projects. She is currently the proprietor of Smart Tech Engineers, where she leads design, engineering, erections, and commissioning of HT-LT systems, substation automation solutions, and large-scale renewable energy installations for reputed clients such as BHEL, L&T, and Schneider Electric. Ms. Sweta Manjare Madam is pursuing her PhD in electrical engineering from National Institute of Technical Teachers Training and Research and holds an MTech in Power System along with professional certification as the Chartered Engineer India, Certified Electrical Supervisor, and ISO 9001 Internal Auditor. Her prior role as technical consultant at Enrich Hydro and senior engineer at Larsen and Toubro have strengthened her expertise in sales engineering, quality assurance, power equipment, and customer-centric project execution with strong technical depth, leadership capability, and industrial exposure. She brings valuable practical insights as an expert speaker in power system, electrical safety, and sustainable energy solutions. Since I am glad to have, we are glad to have such an eminent personality for our today's FDP session, and I would request Mrs. Sweta Manjare Madam to start with her session.
Thank you so much, and I'm really glad to hear about myself. So, and also I really appreciate to all the participants and the FDP panel members for having your presence here after a long tiring day. So I'll not waste your single minute even. So I'll start with my topic, predictive maintenance and fault diagnosis in EVs using machine learning. So how I ended in this topic, because already I'm a research scholar under the research center NITTTR, and my major and broad topic is related to EV only. So I do have my personal interest in this topic. So I used to always read the things and get the innovative ideas regarding this EVs, and also I do some market research also. So as we all know, the automotive industry is rapidly shifting from conventional internal combustion engine vehicles to electric vehicles due to the environmental concerns, a rising fuel cost, and government initiatives. However, electric vehicles are highly dependent on electrical, electronic, and software based systems. Any failure in these systems can directly affect vehicle safety, performances, and reliability. So the traditional maintenance methods are no longer sufficient for these modern e-vehicles. And because of many faults cannot be detected visually or mechanically, predictive maintenance provides an intelligent solution by using real-time data and the machine learning algorithms to predict such sort of failures before they occur. So fault diagnosis further helps in identifying the exact location and type of fault. So in this presentation, I will discuss the importance of predictive maintenance, common electrical vehicle faults, machine learning techniques, and the real world applications, challenges, and the future trends.
Hello, sorry. Once again, you share the
May I
PPT,
please
madam.
request you to reshare the screen?
Pardon?
You have to share the screen. The
Actually,
PPT
I
is not
have
visible,
not
right?
started with my slides yet. I'm just going through the
Okay.
intro. So now I'll begin with
Okay,
my
okay,
slide.
okay.
Yeah.
Okay, fine.
So this is basically a highly relevant topic for engineers because it combines electrical engineering, data science, and the automotive technology. So we'll begin with the introduction to vehicles. In this, we'll cover up the growing adoption of EVs worldwide, need for reliability and safety, role of advanced diagnostics, heavy dependence on electronics, and understanding EVs architecture. So, in electric vehicles, commonly known as EVs, are vehicles that use electric motors powered by the rechargeable battery packs instead of internal combustion engines, which we traditionally use in our fuel consumption engines. Those are our IC engines. So, unlike conventional vehicles, EV do not rely on petrol or diesel and therefore produces zero tailpipe emissions. This makes the environment friendly and suitable for sustainable transportation. Also, worldwide governments are providing much more policies, subsidies, even charging infrastructure developments, and promoting EV adoptions also. So, in an electric vehicle, consists of several advanced components such as lithium-ion batteries, electric motors, power electronic converters, and control units. So these components work together to provide smooth, efficient, and silent operation. However, the heavy dependence on electronics and software makes EV more complex as compared to our traditional vehicles. Small faults in sensors, batteries, or controllers can cause major operational issues. Therefore, intelligent monitoring and maintenance systems are essential here. So, first of all, we need to understand here the EV architecture. Why it is important? Because before discussing any predictive maintenance, it helps to identify where the fault may occur or how machine learning can be applied effectively. So until and unless we don't know the each and every component of EV system, we cannot directly end up on the solution through ML, that is machine learning. So ultimately, why maintenance matters in EVs? Because of the high cost components, safety critical systems, conventional vehicle maintenance, proper monitoring EV in concern to maintenance, and ultimately the customer satisfaction and uptime. Now we'll discuss about these five factors, why these are very much considerable in EV maintenance system. So maintenance is extremely important in electric vehicles because EV components are expensive, sensitive, and safety is very critical. The battery alone accounts for nearly 30 to 40% of the total cost of an electric vehicle. If we are going to lose the battery because of such failures or because of under maintenance, we are going to lose our entire expenses done by hard earned money. So you are going to lose entire 30 to 40% of the total cost in just a single problem of battery. So any failure in a battery system cannot only reduce vehicle's range but also pose serious safety risk such as an overheating or fire. And similarly, failure of electric motor or inverter can cause sudden vehicle breakdown. Suppose you are traveling on a long highway where there is no point of any contact or any service center nearby, and if the some breakdown happens just because of this battery problem, then it will cost you a huge amount to just drag you to the service center, and again you are killing your own time also, which is unacceptable from the safety and reliability perspective. So, unlike conventional vehicles, many EV faults are not visible or audible at early stages. So, degradation occurs internally in batteries, power electronics, and the insulation systems. Without proper monitoring, these faults remain undetected, and even until complete failure occurs, you won't be able to know that this fault has happened. So poor maintenance leads to increased downtime, higher repair cost you may suffer, also reduced customer confidence, because if EVs are not reliable, no one has the confidence to buy it. And even for fleet operators, this can result in a significant financial losses. Therefore, maintenance in EVs must be intelligent, condition based, and proactive. So, predictive maintenance ensures that the faults are detected early, allowing timely corrective actions and preventing catastrophic failures. So, next we'll see traditional maintenance approaches. Now, the traditional maintenance approaches are always like reactive maintenance, preventive maintenance, limitation of conventional methods. We'll see here one by one. So, we'll come to know why preventive maintenance is very much needed compared to this traditional maintenance approach. Traditionally, vehicle maintenance is categorized into reactive and preventive maintenance. Reactive maintenance means repairing the system after failure has already occurred. This approach is really very risky and costly because it leads unplanned downtime and possible safety hazards also. So preventive maintenance follows a fixed schedule, such as servicing after some certain number of kilometers or months. Sometimes service centers also give us a call that it's your scheduled maintenance and you can come back with your vehicle, or will give you a service to bring your vehicle here for such sort of services, regardless of the actual condition of the components. Means you need not to wait for any breakdown happens or any component failures. Prior to that, the maintenance schedule is already fixed in preventive maintenance. These traditional approaches are not suitable for electrical vehicles because EV components degrade differently under varying operating conditions, such as temperature, driving style. I'm saying here that driving style because no one is perfect in the driving. So everybody has their own driving style, and that also affects the performance. And charging patterns. Fixed schedules may result in unnecessary maintenance or missed early stage faults. Additionally, traditional methods rely heavily on human inspection, which cannot detect internal electrical or thermal issues. As EV systems become more complex, traditional maintenance becomes inefficient and unreliable here. That is why I mentioned here the traditional maintenance approaches are not for EV. So this creates the need for advanced data-driven maintenance strategies such as predictive maintenance. So what is predictive maintenance? Here, first of all, for predictive maintenance, we need the database. So data-driven maintenance strategy predict failure before they occur, reduces downtime and cost. So predictive maintenance is an advanced maintenance strategy that uses real-time and historical data to predict when a component is likely to fail. So instead of reacting to failures or following fixed schedules, predictive maintenance monitors the actual condition of the system. So each time, whenever the pre-schedule is decided for the EVs, it is going to monitor the actual condition of the system. So then how it will be monitored? Through the sensors. So sensors continuously collect the data, such as now which are these sensors, how we are going to get the knowledge from these sensors. So the sensor is nothing but your inputs like voltage, current, temperature, vibration and speed. This data is analyzed using machine learning algorithms and to detect abnormal patterns and degradation trends. So these are the things are there as a sensor to collect the data. The key idea behind this predictive maintenance is to perform maintenance only when is required just before failure occurs. Means we need not to wait for breakdown. Before failure occurs, the idea is to prevent excessive cost under this maintenance kind of thing. So this approach reduces downtime, prevents unexpected breakdowns, and lowers maintenance cost. In electric vehicles, predictive maintenance is especially effective because EVs generate large volumes of data during the operation. Because just now, the recent years, we are using EVs and we are collecting the data for different operations for the purpose of machine learning models. And these machine learning models can learn from this data and improve the prediction accuracy over time. So machine learning is not a magic. It ultimately it is using our operational data. It is comparing it with the historical data and the ongoing data. So on that basis only it is working. So predictive maintenance transforms EV maintenance from the reactive process into the proactive process and into the intelligence system ultimately. So this way we are getting an intelligent system. So next we'll see benefits of predictive maintenance in EVs. Now we have seen the predictive, what sort of predictive maintenance is going to happen in EV. Now we'll see the benefits of predictive maintenance in EVs. So improved reliability, lower maintenance cost, and the extended component life. So what these three factors are actually in predictive maintenance? This offers several significant benefits in the context of EVs. One of the most important advantages is improved system reliability. By continuously monitoring vehicle components and predicting faults before they occur, unexpected breakdowns can be avoided. This is especially important in EVs, where sudden failures in batteries or power electronics can compromise the safety also. So another major benefit is cost reduction. Predictive maintenance avoids unnecessary servicing and prevents the expensive repairs by addressing issues at an early stage. So the predictive maintenance also improves vehicle availability, which is crucial for the commercial EV fleets, such as electric buses, taxis, delivery vehicles. Reduced downtime ensures better utilization of vehicles. Ultimately, these commercial fleets are indirectly benefited to all of us. Why? Because they are charging transportation cost comparatively lower than the conventional vehicles. And additionally, predictive maintenance helps extend the lifespan of critical components such as batteries and motors by preventing thermal and electrical faults, reduces the risk of fire or system failure also. So overall, predictive maintenance enhances customers' confidence, which improves sustainability and supports the long-term adoption for EVs. Because whenever we don't have trust in any system or EVs, until unless we got the trust, we cannot buy it or we are not going to buy it. So now, what is fault diagnosis in EVs? The detection of abnormal behavior, identification of fault location, classification of fault types. So fault diagnosis is the process of detecting, isolating and identifying faults within the system. In electric vehicles, fault diagnosis is extremely important due to the complexity and interdependency of the components. Faults can occur in batteries, motors, inverters, sensors, and control systems also. If faults are not diagnosed accurately, incorrect maintenance action may be taken, and which leads to increased cost and safety risk. So, whichever vehicle you are using, at the most important is the safety. First of all, we need to check safety ratings of each vehicles. Then only we should go to buy it. Traditionally, fault diagnosis relies on predefined thresholds and rule-based systems, which are often insufficient for complex EV behavior. Machine learning based fault diagnosis improves accuracy by analyzing historical and real data time patterns. These algorithms can classify different fault types and identify their severity. So effective fault diagnosis enables faster repair, minimizes the downtime, and prevents the fault propagation.
Share the screen.
Madam, PPT is not visible.
Already I have shared the screen.
No, that's why. No. Starting
Now
itself,
see, I'm
not
just
sharing the
changing
screen.
this. I'm just changing the slides. You can see fault diagnosis in EVs.
No. The screen is not visible. Once again, you share the screen.
Okay, let me check. See now, is it visible?
Hmm.
Yes, madam, it is visible, madam.
Yes.
Okay, so effective fault diagnosis enables us for the faster repairs, minimizes downtime, and prevents fault propagation. So the predictive maintenance system, fault diagnosis works together with fault prediction. Somebody has their microphone. Yeah, thank you. So fault diagnosis work together with fault prediction to provide a complete health monitoring solution for EVs. Now the key EV subsystems. What are the key EV subsystems? These are the battery systems, electric motor, power electronics, and the thermal management systems. These are the key subsystems of the EV. Earlier also I said that we need to understand first of all EV architecture, just entire subsystem, so that we can design the machine learning algorithms behind each and every problem or some sort of solutions. So an electric vehicle consists of several critical subsystems that work together to ensure the smooth operation. The battery system stores electrical energy and supplies power to the vehicle. The electric motor converts this electrical energy into mechanical motion. Power electronics such as inverters and converters control the flow of energy between the battery and the motor. And the thermal management system maintains safe operating temperatures for all the components. Here, this is the most important thing to manage the thermal system. After all, this is only going to save your each and every sensor and each and every electrical or electronic components in your EV. So each subsystem has unique failure modes and degradation mechanisms. For example, batteries degrade over time due to the charge and discharge cycles, while motors experience some mechanical wear and tear. And power electronics are very sensitive to this thermal and electrical stress. Because of these subsystems are interconnected, a fault in one component can affect the entire vehicle. So therefore, predictive maintenance must monitor all subsystems simultaneously. You don't have a first come first choice here. You need to monitor entire systems at a time, that is simultaneously. So understanding EV subsystems is essential for designing effective machine learning based fault diagnosis systems. Next, we'll see the battery as a critical component because it has a high cost and degradation pattern, also a safety concern, and even performance dependency. Now we'll briefly see what all 3 points are concerning about. The battery is the most critical and expensive component of an electric vehicle, which you know that because this is only going to consume your 30 to 40% of the cost. So indirectly, it determines driving range, charging time, overall vehicle performance. And right now we are using lithium ion batteries, which are commonly used in EVs due to their high energy density and efficiency. However, they are highly sensitive to temperatures, charging conditions, and the aging effects. Over a time, these batteries experiences capacity loss also and increased internal resistance. So these are the typical problems of the lithium ion battery. So battery failures can lead to serious safety hazards, as we have mentioned here, the safety concern. Ultimately, we are going to use the vehicle if it is safe. Otherwise, why we use it? So battery failures can lead to serious safety hazards such as overheating, fire, or sometimes explosion also. So therefore, continuous monitoring of battery health is essential here. That is why again the predictive maintenance uses battery data such as voltage, current, temperature, and the charge cycles to access battery condition. So again here the machine learning models can predict the battery degradation and identify abnormal behavior early. So this allows timely maintenance and replacement, ensuring safe and reliable EV operations. See, because of this AI tool and the machine learning technologies, we are going to predict about the battery also in current scenario. But in early stages, when we were so like small childrens, at that time, whenever we need to check a battery health, we need to keep it on charging and discharging cycles. We need to observe the time even. And sometimes you have seen those lead acid batteries. For those, we need to monitor the liquid levels of that. So we should be thankful to machine learnings that it has brought us in a stage like it is entirely monitoring the entire battery system and it is giving us the exact condition. It is predicting the battery degradation and the abnormal behavior in early stage. So common battery faults, which are they? Capacity fade, internal short circuit, overheating, cell imbalance. So common battery faults in EVs, those are including all these. So capacity fade reduces driving range and efficiency. Internal short circuits can cause sudden temperature rise and safety hazards. Overcharging and deep charging, discharging accelerate the battery degradation also and reduces lifespan. So cell imbalance occurs when individual cell in the battery pack degrade unevenly, so leading to reduced overall performance. So detecting these faults at an early stage is challenging one using the traditional methods which I said earlier. So machine learning based predictive maintenance analyzes battery sensor data to identify fault patterns. Early detection helps to prevent severe failures and improves the battery lifespan. So accurate diagnosis of battery faults is critical for maintaining safety, its performance, and customer trust in electrical vehicles. Each time I'm mentioning here the customer trust because of the number of things which are unpredictable in EVs. So you are also seeing it in slide by slide wherever the subsystems we are facing in EVs, each subsystem has its own drawback also and benefit also. So next we'll see motor and drive system faults. In this, in motor and drive system, there are few faults like bearing faults, stator winding faults, and the rotor defects. So in electric motor and drive system, these are responsible for converting electrical energy into mechanical motion, making them essential for vehicle movement. Without them, vehicle cannot move. So in electric vehicle, motors operate under varying load and speed and also environmental conditions. And over a time, this leads to different types of faults such as bearing wear, stator winding faults, rotor defects, misalignment, and the insulation breakdown. So these faults can reduce efficiency also and causes abnormal noise and vibration and eventually result in complete motor failure. So motor faults often develop gradually and may not be detected through visual inspection. And if it is left unaddressed, they can cause secondary damage to the power electronics and the mechanical components of EV. So predictive maintenance systems use sensors to monitor motor current, speed, vibration, and temperature. Machine learning algorithms analyze all these signals to detect the abnormal pattern associated with the early stage faults. And the early detection, as I always says, timely maintenance prevents unexpected breakdowns and ensures smooth and reliable vehicle operation. Motor health monitoring is especially important in high performance and commercial electric vehicles where reliability is very critical. Now we'll see here the power electronics fault. Now, what are the major power electronics involved in EV? Those are inverter failures, switching device faults, thermal stress issues. So in power electronics, it plays a vital role in electric vehicle by controlling the flow of electrical energy between the battery, motor and other subsystems. Components such as inverters, converters, switching devices operate under high voltage, high current and high temperature conditions. Due to these rash operating environments, power electronics are prone to faults such as semiconductor switch failure, gate driver malfunction, capacitor degradation, and the thermal stress related damages. A failure in this power electronics can instantly disable the vehicle, making fault detection extremely important. Why? Because your vehicle is nothing if the power electronics of the system fails. Traditionally, protection systems may detect faults only after damage has occurred, as we know that. But since predictive maintenance improves this by monitoring electrical and thermal parameters in real time, so machine learning models can identify early warning signs such as abnormal temperature rise, voltage fluctuations, or switching irregularities. And the early diagnosis prevents catastrophic failures, reduces maintenance cost, and improves overall system reliability. So power electronics fault diagnosis is a key application area for machine learning in electrical vehicles. So this is our most important thing under the fault diagnosis of EVs. Now, who's going to detect these faults? What is the role of sensors in EV and how they are based on? So, the voltage and current sensors, temperature sensors, and vibration sensors. These are the major sensors using in entire EVs. So, sensors are the backbone of predictive maintenance and fault diagnosis systems. In electric vehicles, they continuously measure the critical parameters such as I told earlier also, what are those parameters? Voltage, current, temperature, vibration, speed and torque. These sensors provide real-time information about the operating conditions of various EV components. Without accurate sensor data, predictive maintenance is not at all possible. And here I'll give a small example. Whenever we used to go for the maintenance purpose of our vehicle, forget about the EV, the normal even traditional vehicle also. Those are also having sensors. Without sensors, actually today's vehicle cannot work in an efficient and appropriate manner. So we used to go and tell them that he suggested you that the sensors are under fault, and we are saying that yes, we need to change it so that our vehicle can give a high performance. So what we ask him first, what are the cost of those sensors? Tell us the range. So they define you the ranges from thousands to the lakhs. So what you say? No, my pocket is only affordable for the thousands of rupees. So I can afford the lowest minimum sensor. So now you are going to apply a lowest minimal cost of sensor. So now see what happens if we do such sort of decisions. In modern electric vehicles, those are equipped with the advanced sensor networks integrated with control units and communication systems. High quality sensors ensure reliable data collection, which directly affects the accuracy of the machine learning models. Means here, you yourself are going to fail the AI system because you have chosen the low quality sensors. So, sensor fault, noise, or data loss can lead to incorrect predictions. Therefore, sensor calibration and the validation are also important aspects of EV maintenance. Overall, sensors enables continuous monitoring, early fault detection, and data driven detection making in electric vehicles. So these are the main decision makers who are going to operate your EVs. So decide today what we are going to do in future also and in present also regarding the decisions on the sensors. I just said anonymously here that example because I know every person used to do this thing prior to the maintenance. Now next we'll see the data sources for predictive maintenance. Now we saw the sensors. Now sensors has collected some data, onboard sensors, battery management system BMS, and the vehicle telemetry data. So in predictive maintenance in electric vehicles, entire performance relies on the data collected from multiple sources. Key data sources include battery management systems, motor controllers, inverter systems, onboard diagnostic systems, those are OBDs, and vehicle telemetry units. These systems generate large volumes of data during normal vehicle operation, and data may include electrical measurements also, such as temperature profiles, operating cycles, and environmental conditions. So proper data collection and management are essential for effective machine learning based maintenance. So what we need to adopt ML, that is machine learning here, a proper data and the management, which is a crucial part here to build or design a proper machine learning algorithm. So data must be accurate, consistent, and representative of real world conditions. Historical data is used to train the models, while real time data is used for prediction and diagnosis purpose. So integration of multiple data sources provides a comprehensive view of the vehicle health. The availability of rich data sets, I'm saying here rich data sets. Why? Because we want the exact, accurate, real time and the historical data also for electric vehicles to become ideal candidates for predictive maintenance solutions. Without those, we cannot build in a single shot the predictive maintenance solutions. So we need the accurate data. So what is machine learning? So far we have seen that in entire subsystems, we are incorporating machine learning. So what is machine learning? So ultimately, the machine learning is the branch of artificial intelligence that enables system to learn from data and improve performance without being explicitly programmed. So this is a subset of artificial intelligence, learns the pattern from data and improves performance over time. So instead of relying on a fixed rules, that machine learning algorithms identify patterns and relationships within data it is not relying on the fixed rules like conventional vehicles. Those are relying on the fixed data patterns, like some faults are fixed in the conventional vehicles. But in machine learning, it itself is identifying the different data sets, and different within those data sets, it is finding out the relationship within the data, and it is concluding. So, in electric vehicles, machine learning is used to analyze sensor data and predict the faults or degradation trends. In machine learning models, these can handle large data sets and complex nonlinear behaviors also. This is the utmost benefit of this machine learning, which is common in EV systems. As more data becomes available, these models improve their accuracy over time. Now see here how the data sets are very much important, because it is improving day by day as it is collecting the newer data, and it is improving its accuracy over time. So machine learning forms the foundation of the predictive maintenance and the fault diagnosis by enabling intelligent, adaptive and automated decision making. So its application in electric vehicles represents a significant step forward for a smart and autonomous transportation system. So that is why the machine learning is utmost important in EVs. Now, why we use machine learning in EVs? So why? Because it handles the large and complex data. It detects the early fault. Even it adapts the different models very easily. So machine learning is particularly suitable for EVs, generate which generates large volumes and complex data during the operation. Parameters such as, again, the voltage, current, temperature, speed, vibration vary continuously under the different driving and environmental conditions. Traditional rule-based diagnostic methods are unable to capture these complex and non-linear relationships effectively. That is why we need here machine learning algorithms. On the other hand, it can learn these relationships directly from the data. You need not to teach it. It is directly gaining the relationships from the data itself. So another important reason for using machine learning in EVs is adaptability. As vehicles age, their behavior changes due to wear and tear and the degradation. Machine learning models can adapt to these changes by learning from the new data and ensuring accurate predictions over time. Means it's not like that ki the system, my vehicle has got older and now the machine learning is not able to function it well, or it is not going to happen with my vehicle again. It's not like that. It is learning. It is day by day, it is adapting the things. So that is why I mentioned here adaptive models. It is adapting with your vehicle. So machine learning also enables early fault detection by identifying subtle patterns that indicate degradation, and this reduces overall downtime, improves safety, and lowers the maintenance cost. So overall, machine learning transforms EV maintenance into an intelligent, automated, and reliable system. So that is why we are using here the machine learnings in EVs. So now we'll see the types of machine learning. What are those types? Machine learning techniques are broadly classified into three categories. One is supervised learning, unsupervised learning second, and the third is reinforcement learning. So under the supervised learning, it uses labeled data sets where the output is known. Why we called it as a labeled data set? Because we know its output and making it suitable for fault classification and prediction tasks. So now unsupervised learning, it works with the unlabeled data. Unlabeled data means it used to detect anomalies or unknown fault patterns, which we don't know. In earlier case, we knows those things. In reinforcement learnings, it focuses on learning optimal actions through trial and error base and is used for decision making and control applications because this runs on a trial and error method. So each type of machine learning has its own role in predictive maintenance. Supervised learning provides high accuracy when sufficient fault data is available, and unsupervised learning is useful when labeled data is limited, which is common in EV systems because we know that we do have limited data because it is still under the operating conditions. And understanding these learning types helps in selecting appropriate algorithms for specific maintenance tasks. So earlier also I said that we need to observe the subsystems of the EVs. Then only we will be able to utilize the exact and in an appropriate way the machine learning algorithms. So next we'll see supervised learning for fault diagnosis. Now I earlier also said that we required the proper data sets. Before or after that, we cannot conclude on any algorithms or any data sets. So supervised learning is one of the most widely used techniques for the fault diagnosis purpose in EVs. It requires the labeled data sets that contain examples of normal and faulty conditions. Means ultimately the system is going to compare. It is going to find out the relationship between the data sets, that when the fault has occurred or when was the normal system. Those entire data it is continuously monitoring. So using this data, machine learning models learn to classify faults and predict system behavior. Common supervised learning algorithms include support vector machines, SVMs, decision trees, DTs, and the random forest, RFs, and the neural networks. So such sort of common algorithms have been used for EVs and are going to help in future model purposes also. The main advantage of supervised learning is high accuracy, reliable fault classification. However, this collected labeled fault data can be a challenging in EVs because I said the daily operational data has been collected from the EV systems and the fault is very rarer in EVs and we cannot reproduce those faults just to analyze and just to study it. That is the main drawback of the system because if we'll reproduce it, it is going to cost us much more than that vehicle cost. So these faults are rare and costly to reproduce. So despite this limitation, supervised learning remains highly effective for diagnosing known faults. It plays critical role in battery fault detection, motor fault classification, and inverter diagnosis. So this way, the labeled one, the supervised learning for fault diagnosis can give a vital role in the EVs. So the next is unsupervised learning for anomaly detection. Now, unsupervised learning does not require labeled data. We heard earlier also, making it suitable for detecting unknown and new faults. These algorithms learn the normal behavior of the system and identify the deviation from this behavior as anomalies. Means it is taking inputs from the system itself. Whether the earlier this was the condition and was that condition was normal or abnormal. So common unsupervised techniques include clustering methods and autoencoders. Now these are also the type of your machine learnings, the clustering method and the autoencoders. So these are going to help in unsupervised learning. In electric vehicles, the unsupervised learning is particularly useful during early deployment stages when the fault data is limited, because we don't know now what sort of fault is going to happen, because those are very rare faults and we cannot reproduce them. So it helps to detect abnormal behavior in batteries, motor, and power electronics. So all these key subsystems, it is going to help us for the fault detection purpose. And the unsupervised learning enhances system reliability by identifying faults those are not previously known or modeled. See, means so far we have not concluded that this type of fault is going to occur. This is very useful in case of unknown faults. Now next we'll see the common machine learning algorithms used in EVs. Various machine learning algorithms are used in predictive maintenance and fault diagnosis of electric vehicles. Linear regression is used for trend analysis, means what sort of the fault trend is, what sort of normal data set trend is. So such sort of analysis and degradation prediction, that vehicles components are degrading by after use over a period of time. So support vector machines are effective for classification of tasks, what sort of task we need to classify, for that SVM is going to use. In decision trees and random forest provides interpretable models with good accuracy. And the neural network handles complex nonlinear data and the relationships. The choice of these algorithms depends on the application, data type, computational constraints, and selecting the right algorithm is essential for the accurate and reliable maintenance system. So machine learning algorithm enables intelligent monitoring and proactive maintenance in electric vehicles. So ultimately the neural networks in EV is going to diagnose further more things like ability to model nonlinear behavior used for complex systems, high prediction accuracy. Now, neural networks are one of the most powerful machine learning techniques used in electric vehicle diagnosis. They are inspired by the structure of human brain. Neural networks consist interconnected layers of different processing datas in EV. Systems many ensures the relationship between the different variables such as voltage, current, temperature, and the speed. And these are highly non-linear ones, which handled by neural networks. And neural networks are well suited to model these complex behaviors very accurately. So in fault diagnosis, the neural networks learn from historical sensor data. Those are collected by different sensors during both healthy and faulty operation conditions. Once they trained, they can identify fault patterns in real-time vehicle data. And the neural networks are widely used for battery health estimations, motor fault detections, and inverter diagnosis. Their ability to process multi-sensor data simultaneously. Earlier also said that we cannot apply one by one solution or one by one processing of the data. It needs to be done simultaneously. And here the neural network is providing us that facility to simultaneously process the data. So it makes them highly effective for EV application. Although neural network require large data sets and computational resources, their accuracy and adaptability make them a key technology in predictive maintenance system. So that is why neural networks are the are the most important things in EV fault diagnostic systems. Shortly, in ML, deep learning is also the part of main artificial intelligence for the EVs. So here the major convolutional neural network it handles, and the recurrent neural network it handles, and the handling time series data also. So in deep learning, it is an advanced form of neural networks. Why we are covering this deep learning here? Because it is related to the neural networks, and that uses multiple hidden layers to extract high level of features from the raw data. And it is particularly effective for handling large data sets and the complex systems such as electric vehicles. The deep learning models automatically learn important features and reduces the need for manual feature extraction. It itself extracts the feature from the system. In EV predictive maintenance, the convolutional neural networks are used for vibration and image based diagnostics. And here it is very much necessary because we are using right now in market, it is too much widely used sensors as image based diagnostics. While recurrent neural networks are used for time series data such as battery voltage and current signals, deep learning enables highly accurate fault prediction and early warning systems. However, deep learning models requires high computational power and large training datasets. Despite these challenges, deep learning is increasingly adapted due to its superior performance and the ability to support real-time diagnostics in EVs. So next we'll see battery state of health estimation. Now, earlier also I said the battery is going to consume our 30 to 40% of the cost. So we need to monitor the battery state of health also. So state of health, commonly known as SOH, it is critical parameter that indicates the overall condition of an EV battery compared to the new battery. And the SOH reflects capacity loss, internal resistance increase, and the aging effects. So the accurate SOH estimation is essential for predicting the battery lifespan and the planning maintenance. So traditional SOH estimation methods are often inaccurate under different varying operating conditions. Machine learning here again going to help us to, after modeling it, analyze the historical charge discharge cycles. It will observe the temperature data and the voltage behavior also to estimate the overall SOH more accurately. That is, the battery state of health is how it is more accurately. For that purpose, again, it is going to help us. So, the predictive maintenance system uses battery state of health estimation to prevent unexpected battery failures and improve the safety also. So accurate SOH monitoring ensures reliable vehicle operation and supports efficient battery management. So next we'll see battery state of charge estimation. Now we saw that state of health. Now we'll see here the state of charge estimation. The state of charge, that is SOC, we denote it with the SOC, represents the amount of energy remaining in the battery at a given time. Accurate SOC estimation is essential for predicting driving range and preventing overcharging or deep discharging. This traditional method, whereas in traditional method, we always struggle whether the charging, discharging or deep discharging, what is the current state, that is the SOC. We generally don't know about those. But in this dynamic world, with the help of machine learning, we can estimate those also. And since we do have some dynamic driving conditions, we need to know that what sort of kilometers the battery charge is having right now, how much kilometer we can travel, or where I need to charge my battery. If the deep discharging occurs, then what I'm going to face. These entire things can be improved by machine learnings. So SOC estimation by learning from real-time sensor data and adapting to changing conditions. Like as I said, at what state my battery is, that condition should be known to each one who's ever operating these EVs. So improved SOC accuracy enhances driver confidence and the battery safety. Reliable SOC estimation is the key component of the intelligent EV management system. So next we'll see the motor fault detection using ML. Motor fault detection is a crucial for maintaining EV performance and the reliability. So machine learning models analyze motor current, speed, vibration, and temperature data to detect the faults, such as bearing wear and the winding damage. In early detection, it prevents severe failures and reduces the downtime, just because of this ML based motor diagnostic ensures, because it is ensuring us so efficient and safe vehicle operation, making them an essential part of predictive maintenance system. Next we'll see the vibration analysis for fault diagnosis. Now the vibration analysis is one of the most widely used techniques for fault diagnosis in the rotating components such as electric motors and the bearings in the electric vehicles. When the motor operates normally, it produces a specific vibration pattern, which we can feel also, and which system is also collecting the data that what is the normal vibration of the motor when it is under normal running condition. So, however, faults such as bearing defects, misalignments, imbalance, or rotor damage causes changes in the vibration characteristics. So, the system is already collecting data. It knows what is the normal vibration and what is the abnormal vibration characteristics when such sort of fault causes the changes. So these changes can be detected much earlier than those are visible or audible symptoms. Such as in electric vehicles, the vibration sensor, and those are accelerometers, are mounted near the motor or the drive systems so that they can sense the vibrations. These sensors continuously record vibration signals during vehicle operation. So it is collecting the raw vibration data, but this is very complex data and cannot be interpreted directly. So we need to extract some features out of it. So therefore, the signal processing techniques such as time domain and the frequency domain, these two analyses are applied here. Why? Just I said that we need appropriate signals to fetch to the system. Those are complex raw data. We need to extract the mean required signals out of it. So we are using here the time domain and the frequency domain analysis. In machine learning algorithms, we fetch to it, then it analyzes the extracted features to classify the normal and the faulty conditions. Ultimately, we have collected the data. Again, we have extracted the exact one which we required for the analysis, and we fetched it to the machine learning. So again, the machine learning will classify it whether it is a normal or the faulty conditions. In predictive maintenance system, uses the vibration analysis to detect these early stage mechanical faults before they become severe. And this helps to prevent sudden motor failure and reduces the repair costs, but obvious, and it improves vehicle reliability. So the vibration based fault diagnosis is especially important for high speed motors used in modern electric vehicles. Now we'll see the thermal fault diagnosis. In thermal fault diagnosis, it is critical in electric vehicle. Why? Because the excessive temperatures can severely damage the batteries also, motor also, and the power electronics part. So the components in EVs operate under high electrical and mechanical stress, which generate heat. If this heat is not managed properly, it can lead to insulation failure, component degradation, sorry, or even thermal runaway in batteries. So the thermal fault diagnosis involves monitoring temperature data, which is collected from the sensors. Those are placed on the batteries, motors, and inverters. So the machine learning models can analyze the temperature trends and correlate them with the operating conditions such as load, speed, and these may be the varying conditions like different loads, different speed, and the different ambient temperature also, because we face the three seasonal temperatures. Under the summer condition, the ambient temperature will be different. Under the environmental temperature will be different. Under the rainy season, it will be different. Under the winter season, it will be different. So for abnormal temperature rise often indicates early stage faults such as cooling system failure, increased internal resistance, or switching losses. So ultimately, in predictive maintenance, it uses the thermal fault diagnosis to generate early warnings and activate the protective measures such as reducing load or improving cooling. Early detection of thermal issues significantly improves the safety and reliability of the electric vehicles and prevents the catastrophic failures. So such way we need to address these thermal faults also through the machine learning models which are going to use us, which are going to save the EVs from the thermal fault. Next, we'll see the feature extraction techniques. Earlier in the other slide, we saw that the feature extraction process, that the raw data is collected and we extracted some important signals, data sets with the help of time domain features and the frequency domain features. So we'll see here shortly. Feature extraction is a crucial step in machine learning based fault diagnosis. The raw sensor data collected from EV systems is often noisy, high dimensional, and complex. So feature extraction converts this raw data into meaningful one. And the compact representations of such signals, those highlight the important characteristics of the system behavior. So the common feature extraction techniques include time domain features such as mean, variance, and the RMS values, and frequency domain features obtained using Fourier transforms, and the time frequency features using wavelet analysis. So proper feature selection improves machine learning model accurate and it reduces computational complexity. So ultimately in predictive maintenance system, effective feature extraction helps to differentiate between the normal and the faulty conditions. And it plays a key role in battery diagnostics, motor vibration analysis, and thermal fault detections. So without proper feature extraction, even advanced machine learning algorithms cannot perform effectively. So that is why here the feature extraction techniques are also utmost important. Now we'll see the data processing. Now we have extracted the features also, we have gathered all signals also. Now how it is going to fetch to the machine learning? So for that we need data processing system. So the data processing is an essential step before training machine learning models for predictive maintenance. Real world EV data often contains noise, missing values, outliers, and the inconsistencies. If such data is directly used it can lead to inaccurate predictions and the false alarms. For that purpose, we always need data processing before modeling any machine learning models. So data pre-processing involves cleaning the data, removing noise, handling missing values, normalizing data ranges, and filtering out irrelevant information. So to avoid such sort of false alarms and inaccurate predictions. In electric vehicles, data processing also includes synchronizing data from multiple sensors and the systems. I said na ki at a time it should act simultaneously because number of sensors are there. If one sensor is giving such sort of input and other sensor is giving such sort of input, but both are working on a same time frame or same time zone. So for that, these needs to be synchronized also to give you the accurate output. Again, the proper pre-processing ensures that machine learning models learn meaningful patterns rather than random noise. It significantly improves prediction accuracy and reliability. So data pre-processing is especially important for real-time EV applications where the incorrect predictions can impact safety and the performances. So this way the data pre-processing is needed for the accurate results to fetch to the ML. Now we'll see the training machine learning models. Now we have got all the sensor data, we have featured, extracted also, we have got the time domain and frequency domain outputs also, we have data pre-processed also. Ultimately, why we are doing this? To train the ML models. So what is needed in this stage? Training machine learning models involves feeding pre-processed data into selected algorithms so that they can learn the patterns associated with the normal and the faulty conditions. During training, the model adjusts its internal parameters to minimize prediction error. A well-trained model can accurately predict faults and the degradation trends in EV components if we do such things. Training requires sufficient and representative data. Why? Because we saw that earlier also what happens with the false alarms and the inaccurate faults. To avoid that, it requires sufficient and representative data covering the different operating conditions. Validation and testing are used to ensure that the model generalizes well and does not overfit the training data. See, here we are not directly implementing these ML models after training also. Why? Because each and every model should validate itself that it is proven that it is much effective to apply directly in the EVs. So in predictive maintenance systems, trained models are continuously updated using new data to improve the accuracy over time. As I said, the day by day, the operation conditions are getting different and we need to adhere those also. So for that, the upgradation is also utmost important. So the proper training of machine learning models is the foundation of reliable predictive maintenance and the fault diagnosis in the electric vehicles. So next we'll see the model evaluation matrix. After training the machine learning model, it is very important to evaluate its performance before deploying it in real electric vehicle systems. As I told you, why we are not going to apply it? Because we don't know the exact outcome of it. So the model evaluation matrix helps us understand how accurately the model can predict faults and how reliable it is in real world conditions. Common metrics include accuracy, precision, and recall, and the confusion matrix. So, accuracy tells us how often the model makes correct predictions, but it alone is not sufficient for the safety and the critical systems like EVs. The precision indicates how many detected faults are actually correct. And while this recall shows how many real faults the model successfully detects. In EV maintenance, missing a fault can be very dangerous. So high recall is often more important than high accuracy. So why? Because recall is going to show us the real fault in the model. It detects the real fault. So we required here recall than the accuracy. So confusion matrix helps here to visualize correct and incorrect predictions. It is also important. We need to actually see whether the correct and the incorrect predictions, which are they. So the proper evaluation ensures that the machine learning models provide trustworthy fault diagnosis and do not generate any excessive false alarms or missed detections. So that is why the model evaluation matrix is also important here. Now we'll see the deployment in EVs. So far, we have seen that the different techniques, how we landed on the ML models, and how we evaluated through the matrix, how we evaluation done of the models. So now the part is deployment in electric vehicle systems. So deployment refers to integrating trained machine learning models into real electric vehicle system. So far we studied the EV subsystems, then machine learning types, then machine learning different techniques which are going to help to build the machine learning model. And now we are going to deploy it here. So this is a critical step because models must operate reliably under real-time constraints. So machine learning models can be deployed on onboard vehicle controllers, edge computing devices, or on the cloud-based platforms, depending on systems requirements. So onboard deployment enables real-time fault detection without internet dependency, while cloud deployment allows powerful computation and the centralized monitoring for fleets. Edge computing offers a balance between latency and the computational capabilities. During deployment, factors such as processing speed, memory limitation, energy consumption, and the system safety must be considered. Proper deployment ensures the continuous monitoring and timely alerts, also the effective predictive maintenance in EVs. So, in deployment, we saw the different characteristics of the after deployment conditions, that what we are going to face ultimately when uses the actual machine learning models on the real time EVs. So next, now we will be going to face some challenges also. Those challenges in predictive maintenance, because we do have limited label data quality issues, and the computational constraints. Despite its advantage, the predictive maintenance in electric vehicle faces several challenges. Now, what are they? One major challenge is the limited availability of labeled fault data, as the real faults are very rare and expensive to reproduce. So, data imbalance between healthy and the faulty conditions can affect the model accuracy. Another challenge is data quality issues. The sensor noises, missing data, and the faulty sensors can lead to incorrect predictions. Now, the computational constraints. In computational constraints, when it is used in onboard systems, it also limits the complexity of the machine learning models. Additionally, variations in the driving behavior, the environment, and the vehicle usage make this modeling very difficult. And overcoming these challenges is essential for reliable and scalable predictive maintenance systems. Furthermore, now we have involved entire AI and machine learning tools here. The cybersecurity concerns will be there. Now, what are the cybersecurity concerns? In these modern vehicles, these are highly connected systems that rely on data exchange between the sensors, control units, and the external networks. This connectivity introduces cybersecurity risks. Unauthorized access or data manipulation can lead to incorrect fault predictions or even unsafe vehicle operations because we are connected through the AI systems. Machine learning models themselves can be targets for the cyber attacks, such as data poisoning or adversarial attacks. Therefore, secure data transmission, encryption, and the authentication are essential. Ensuring cybersecurity protect vehicle safety, user privacy, and the system integrity. Sometimes we see na in our mobile phones also randomly we choose apps. We say that are why are this app is going to feel me better or it is giving me a some sort of playing games or something application wise or application oriented wise it is better and it is useful. We are avoiding those data privacy things. We are clicking all the buttons and we are selecting and we are downloading it. But ultimately, why we should not go for that? Just because of this cyber security system. And once we have entered this EV into the AI based system, already we are under the scrutiny by the cyber crimes. So the cyber security must be integrated into predictive maintenance system from the design stage. So the real-time implementation issues. Now, what are the real-time implementation issues? Real-time fault diagnosis in electric vehicle requires fast data processing and immediate decision making. Machine learning models must operate within strict time constraints to ensure safety, latency, and limited computational resources and energy consumptions are major challenges here. So, onboard hardware may not support complex deep learning models. Therefore, lightweight and efficient algorithms are required. And the balancing accuracy with real time performance is crucial. Effective real-time implementation ensures timely fault detection and reliable vehicle operation under all the circumstances. So the simple case study here is for battery fault prediction. In this case study, the predicting battery faults in electric vehicles using machine learning techniques. Batteries are the most critical and failure prone components of EVs. So early fault prediction is extremely important. And in this case, study data was collected from the battery management system, which includes voltage, current, temperature, and state of charge, and the charge discharge cycles. And the historical data representing both healthy and faulty battery conditions was used. So this way, the battery case study for the input data, like collected data, have been gathered. Now, in machine learning models such as neural networks or random forest were trained on these data sets. Now, we have collected the data sets. For that, we have chosen the neural network and the random forest. So, they were trained for these data sets to identify abnormal patterns. The model successfully predicted faults such as overheating, internal resistance increase, and the capacity degradation. Well, before actual failure occurred. So compared to traditional threshold based methods, the ML based approach provided earlier warnings and higher accuracy. The results showed a significant reduction in the unexpected battery failures and the improved safety. This case study demonstrates the practical effectiveness of the predictive maintenance in real EV applications. It also highlights how data-driven approaches can extend battery life, reduce the maintenance cost, and increase user confidence in electric vehicles. Now we'll see a short example of case study for motor fault diagnosis here. In this, the application of machine learning for diagnosis fault in electric vehicle motors. Motors operate continuously under varying load and speed conditions, making them susceptible to gradual degradation. In this study, motor current, vibration, and temperature data were collected during vehicle operation. After that, the signal processing techniques were applied to extract the relevant features from the raw sensor data, because we are not getting the exact sensor data through the vibration, temperature, or the current. So machine learning models were then trained to classify different fault conditions such as bearing faults, rotor imbalance, and the stator winding issues. The machine learning based system successfully detected faults at the early stage, even before noticeable performance degradation occurred. So the result showed reduced downtime, lower maintenance cost, and improved motor reliability. This case study highlights the importance of predictive maintenance for drive systems and demonstrates how machine learning enables the accurate and timely fault diagnosis in the electric vehicles. So next we'll see here the integration with BMS, the enhanced decision making. So integration of predictive maintenance system with the battery management system or BMS significantly enhances battery monitoring and control. The BMS already performs functions such as SOC estimation, we saw that, the cell balancing and protection. So by integrating machine learning models, the BMS is becoming more intelligent and adaptive. So ML based predictive maintenance allows the BMS to predict battery degradation and detect the abnormal behavior and optimize the charging strategies. This integration enables proactive decision making instead of reactive protection. It also helps in planning maintenance and replacement schedules more effectively. An intelligent BMS improves battery safety, extends its lifespan, and enhances overall EV performance. So ultimately, it is a key step toward a smart and autonomous electric vehicles. Next, the digital twin concept. We shortly see here what is the digital twin concept in this machine learning process for the fault diagnosis. A digital twin is the virtual replica of a physical system that continuously receives real-time data from the actual system. In electric vehicles, digital twins are used to simulate the behavior of batteries, motors, and power electronics. Why? Because each time we cannot go and apply on the real vehicle, right? So digital twin concept is here just to give us the answers when we apply what will happen. So machine learning models enhances digital twins by enabling accurate predictions and the fault analysis. And it allows engineers to test the different operating scenarios without risking the physical damage. See, because whichever model we are going to build or the algorithm which we are going to design, those we cannot put exactly on the EVs. Now, for that, digital twin concept is there, and they help to predict failures, optimize maintenance schedules, and improve the system designs. In the predictive maintenance, digital twins provide a powerful platform for continuous health monitoring and the decision support. So, this plays the very much important role in the future of the smart mobility. Now, the role of IoT in EV maintenance. So, the Internet of Things. This is IoT is nothing but the Internet of the Things, which plays very crucial role in predictive maintenance of electrical vehicles. Because IoT enables connectivity between the vehicles, sensors, cloud platforms, and maintenance systems. Through IoT, the real-time data from EV can be transmitted to centralized servers for analysis. See, up till now we were limited to just to the vehicle. Whenever the software version is there, or we are feeding to the system directly into the EV. But now through the IoT, we are directly connected to the centralized servers for analysis purpose. So whatever problem the EV is going to face, ultimately we are connected to the centralized system. So this connectivity allows remote monitoring, fault analysis, and software updates. For fleet operators, IoT enables predictive maintenance across multiple vehicles, reducing downtime and operational costs. So IoT also supports continuous learning of machine learning models by providing fresh data. So what we say here, overall, the IoT enhances the scalability, connectivity, and intelligence of EV maintenance system. And it is also a key enabler for smart transportations. Now we'll see the future trends here. Now, future trends in EV predictive maintenance. The future trends in electric vehicles is closely linked with advancement in artificial intelligence, connectivity, and the computing power. As electric vehicles become more intelligent, machine learning models will shift from basic fault detection to fully autonomous health management systems. Future systems will continuously learn from the real world data only, but and will adapt also to the changing driving patterns and even the environmental conditions and the user behavior also. But ultimately it is going much more advanced than it is at the existing systems. So advanced deep learning models such as transformer architectures and the hybrid physics informed models will provide more accurate predictions. Edge AI will allow complex models to run directly on vehicles, enabling faster decision making without relying on cloud connectivity. So ultimately, in predictive maintenance, it is going to be a cost effective electric vehicles in future. So what are the research opportunities and the scope? In predictive maintenance, in electric vehicle, it offers vast research opportunities for engineers and the researchers. Which area are those? Those are under development. Those are robust machine learning models that can perform well within limited labeled fault data. And semi-supervised and unsupervised learning techniques are gaining importance in this domain. Another key research direction is explainable artificial intelligence. Since EVs are safety critical systems, it is important to understand why model predicts of, and the research is interpretable models will increase trust and acceptance of ML based maintenance systems. So energy efficient algorithms suitable for onboard implementation also represent an important research area. So what is environmental and economic impact on EVs for the fault diagnosis systems? The predictive maintenance using machine learning has significant impact on the electric vehicle industry because it reduces the unexpected failures, improves safety, and enhances the customer satisfaction by detecting faults early. Manufacturers can minimize warranty cost because of this benefit and improve the product reliability. For fleet operators, the predictive maintenance reduces vehicle downtime, so low maintenance expenses. and it enables the data-driven decision making for asset management. So overall, predictive maintenance supports large-scale EV adoption by addressing the reliability concerns and improving the total cost of ownership. It plays a key role in making electric vehicles more dependable and economically viable. Now, the comparison with the ICE vehicles, the predictive maintenance in electric vehicles differs significantly from the maintenance in internal combustion engines. Those are ICE engines. ICE vehicles have many mechanical parts and that require frequent servicing, while EVs rely more on electrical and electronic components. And the traditional ICE maintenance is largely reactive, schedule based, whereas EV predictive maintenance is data driven and proactive. So this shift from mechanical to intelligent maintenance represents a fundamental transformation in the automotive industry. So EVs require fewer physical inspection but more advanced software and data analysis capabilities. So next we'll see the advantages of ML based approach. So machine learning based predictive maintenance offers several advantages for electric vehicles. It enables early fault detection. Also, it has got much more adaptability. By predicting failures in advance, maintenance can be scheduled efficiently and avoiding unexpected breakdowns. So in conclusion, machine learning plays a vital role in future for electric vehicle maintenance and support development of the intelligent and the reliable and sustainable transportation systems. Next, we see the limitation of machine learning based predictive maintenance. It has got some limitations also. So far, we have seen the benefits and the advantages. So while machine learning offers powerful tools for predictive maintenance in electric vehicles, it also has certain limitations that must be acknowledged. One major limitation is the dependency on large amounts of high quality data. A machine learning model requires extensive historical data to learn the accurate fault patterns. However, in real world EV applications, fault data is often limited, incomplete, or imbalanced since failures are relatively rare events. Another limitation is model generalization. A model trained on data from one vehicle model or operating condition may not perform well on the another one due to differences in design, usage patterns, environments, and the computational constraints also. So especially on-board implementation where the processing power and the energy availability are limited, here the limitation comes. So additionally, many machine learning model functions as a black boxes, making it difficult to explain their predictions. So these limitations highlight the importance of careful model selection, validation, and the continuous improvement. So these understanding these challenges, which helps engineers design more reliable and trustworthy predictive maintenance system. So next we'll see the industry adoptions. So in the industry adoptions, the researcher, we see the automotive manufacturers, fleet operators, and the research institutions. The industries are very much needed for EVs because the growing business of EV is ultimately going to help us to enhance the EV business and the utilization of the EVs for the research institutions also, and for the industrial adoption also, and the moreover the fleet operators also, because it is utmost benefited to the fleet operators. So conclusion is In conclusion, the predictive maintenance using machine learning represents a major advancement in electric vehicle technology. By leveraging sensor data and the intelligent algorithms, EVs can detect faults in early stage and prevent the costly and dangerous failures. Machine learning transforms maintenance from a reactive process into the proactive and intelligent systems. Although these challenges such as availability, computational constraints, and the cybersecurity remains, and ongoing research and technological advancements continue to address these issues. So the integration of machine learning with EV systems contributes to increased reliability, safety, and sustainability. So the predictive maintenance is not just technical improvement, but a key enabler for the future and the smart mobility. And it will play a crucial role in building trustworthy and the efficient electric transportation system. So thank you for your attention and time. Through this presentation, we have seen how predictive maintenance and the fault diagnosis using machine learning can significantly improve the performance, safety, and reliability in electric vehicles. I hope this presentation has provided a clear understanding of the concepts, technologies, and the practical applications involved. So I would now be happy to answer any questions or discussion any part of the presentation in more detail. Please please feel free to ask questions related to the machine learning techniques, electric vehicle components, and the real world implementations. Thank you once again. Praveen sir.
Dear participants, if you have any questions, any queries, you can just unmute your mic and ask the questions.
Hello, madam.
Yeah, hello, please.
Yeah, you said every time ML algorithms are used. Can you please give us the result of at least some of the case studies?
Just a minute. Just hello.
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 Yes, madam.
Yeah, yes, ma'am. Please.
So you couldn't hear the question?
Yeah, I could not hear. Please.
Yeah, it's okay, madam. I'll
yeah.
repeat it.
Yeah.
What I was asking is, ML models are used in many, in your case studies. That's what I heard. Okay.
Yeah.
At least I want to know which ML models were used for BMS and what is the result that you obtained?
For BMS, madam, directly we haven't applied on it. We used for battery itself. So for battery, the RF and SVM techniques we have been applied. And
Okay.
from those, the exactly time domain and the frequency domain. These two techniques we have been applied for the feature extraction purpose.
Okay.
Yeah.
What is the platform you have used, madam, for doing the programming?
Simulation.
Simulation in MATLAB or in Colab?
In MATLAB itself.
Okay. And
Yeah.
the data that is taken, live data or real-time data or some data from some website?
Actually, we are visiting few service centers here for the EV fleets and the other vehicles also. So from them, from the service engineers itself, we have taken some feedbacks. And over that only we are utilizing, because see, just now the EV has been started and there are few cases reported on this BMS system, that the battery management systems and the failure of battery. Only few countable cases are there, and those some cases are because of the temperature rise also, because of the heating problem and thermal stress also.
Okay, madam. And then you have done the case studies on each and every component of the entire EV system?
No, madam, yet not.
Not yet. Then
Right.
which were the components on which you tested?
Actually, we are working on the design of the controller itself. So this
Okay.
is a by part of it. Studying
Okay.
the fault diagnosis and all things. Whenever you are designing any controller for the EV system, you need
Hmm.
to first of all understand the complete subsystems, and after all, we need to conclude on the controller's requirement. Until unless we
Mhm.
don't know the exact EV's system problems or the faults associated with it, we cannot design the controller.
Okay, madam. Okay,
Yeah,
okay. Thank you.
right. Okay, if you don't have any further questions, I do have few more slides with me, which are going to enlighten you. If you allow me, can I show you that?
Actually, time is over basically. Okay, got 20 minutes extended.
I'll explain within a minute or 2 minutes also, because see,
Okay.
what I have said is we are actually visiting the real market conditions. So in this, the right now we are having the ADAS level 2 work here. So what it is working with it, that the lane keeping assistant, maybe some of you have seen, this is actually present in our EVs. In recent cars, we are getting these features right now. So these are all AI driven and machine learning driven. So madam just now spoken with me, she can also get some few ideas over here, so that she can work further more on the on these topics. So the adaptive cruise control, already it is there in the present market. Already we are using it. The lane centering assist is also there. It is working with us through the radar and camera systems, and how it works through the sensors, the obstacles and slower moving vehicles in front. With those system inputs, it is helping. Even it avoids the front collision, it avoids the rear collision also. Also, it is assisting you in inner traffic systems. It is giving you smooth conditions. Along with that, the stressful, you can avoid stress roads that you can, even it cannot allow you to cross the lane, because it is giving you the lane assistance also. It ultimately it saves the fuels and the better result value also. Again, it is providing you the 360-degree views on the road, and it is continuously monitoring the lane departure warnings. So in during heavy rain and fog and dust condition, sensors may affect, but it gives you reliable functions. Ultimately, it is a driver's role to keep you continuously in attention mode, so that complete reliability should not be on the vehicle. And as I said you, wherever you got stuck, it provides you the 360-degree coverage for the surroundings, and it gives you the 3D object detection and resolution also, and the clear vision in even in a bad weather and low light also. So real-time data processing is giving you the assistant here, and instant alert it is providing currently in the vehicles. So thank you once again.
Thank you. Thank you. Is this sir? One minute,
Yes, sir.
madam. Mr. Sir?
Yes, yes, sir. Is that audible, sir?
Yes, yes, audible.
Hello?
Yes, audible. Please continue.
Okay, okay, sir. Okay. On the behalf of ATAL FDP organization team of DKT Society Textile and Engineering Institute Itlaganji and all the participants, I take this opportunity to express our sincere gratitude to Mrs. Sweta Manjare Madam for delivering an insightful and enriching session on predictive maintenance and fault diagnosis in EVs using machine learning. Ma'am, your session provides a clear understanding of how machine learning technique can be effectively applied to predictive maintenance in electrical vehicles, enabling early fault detection, improved reliability, and enhanced system performance. The way you connected theoretical concepts with practical application in real-world scenario, the topic highly encouraged and relevant, especially in the context of emerging EV technology. We would also like to thank ATAL for providing us such a wonderful platform through this FDP. Once again, we extend our hearty thanks to Mrs. Sweta Manjare Madam for sparing her valuable time and making this session a great success. Thank you, Madam.
Yeah, thank you so much.
Thank you, madam. Thank you.
Thank you, sir.
Now I declare that the today's session is over and all the participants can leave the meeting now and we'll meet tomorrow.
Thank you, ma'am.
Yes, thank you.